So without further ado, we're going to hand things over to our special guest tonight, Dr. David Grinspoon.
Thank you very much. Great to see you here tonight and to be in this amazing dome to talk with you for a little while about one of my favorite subjects, comparative planetology, and what we can learn about our home planet through studying the other planets that will hopefully help enlighten us about how our own planet works and help us do a better job of managing ourselves and making a good future for our species and our biosphere here on our home planet. As mentioned, I do comparative planetology and astrobiology. What that means is I'm a member of several teams that propose and, when we're lucky, get selected to build and fly spacecraft to other planets and try to learn about the atmospheres, the surfaces, the interiors, the climates of our neighboring planets, and sort of reconstruct their stories, their histories, and understand, among other things, the astrobiology part is understand where else in the universe and where else on other planets might be good homes for life. And a lot of that has to do with climate evolution, because ultimately climate is what determines the conditions on a planet that may be or may not be suitable for life. But obviously, climate evolution also pertains very much to our current challenges we're facing as a civilization here on Earth. So that's there's an interesting connection there between astrobiology and between sort of human wisdom about protecting our civilization and our biosphere. So that's those are some of the connections I want to talk about this evening. If I can have the first slide, please. So, you know, we live in this extraordinary time where we're really just beginning to explore the universe beyond our planet. And in our own solar system, we're able to do that directly by sending spacecraft to our neighboring planets. And that enables us to start doing comparative planetology, where we see the stories of the planets, not just in isolation, but as a set, as a family. And just as in any family, the similarities and the differences among the siblings are illustrative in various ways. And it's a big solar system, but I'm going to focus tonight on my sort of favorite trio of worlds, which is Venus, Earth, and Mars. And I love the comparative study of these planets because Venus and Mars are not only our nearest two neighbors in the solar system, but they're also in many ways the two planets most similar to Earth. If you ask me which planet in the solar system is most like Earth, I'll say, well, in some ways Mars, in some ways Venus. Mars is a place that we often think about going, and we're thinking about sending humans in the near future. And we're fascinated with exploring because in terms of surface conditions, it's in a way most similar to Earth. It's a place where we could probably go and set up shop on the surface. Venus is a planet that in some other respects is the most Earth-like place. It's almost exactly the same size as Earth, and that's pretty amazing in a whole solar system of not just the 8 or 9 planets in our solar system, depending, or 1,000, depending on how you're counting. But now in the billions of planets we know in the galaxy, or we know about, we can infer because we've been discovering the exoplanets beyond our solar system, but we don't know of any two neighboring planets that are basically the same size like Earth and Venus. And so they're the same size, they formed around the same time, and in many other ways they're kind of twin planets. They seem to be the same density, made out of roughly the same stuff, and yet they've evolved to very, very different states at present. Venus is, I'll talk a little bit more about that, but it's a hothouse, dried out oven of a planet, very different from our comfortably warm, wet, oceanic Earth. So I want to talk now a little bit about climate, what climate is, and how we've learned about the differences in climate of these planets, how they've evolved, and what that can tell us about climate change on our home planet. So the first thing to think about is these 3 planets orbiting the sun. If I could go to the next graphic, please. Of course, their comparative orbits, Venus, Earth, and Mars. Venus, it roughly orbits about 3/4 of the way from the sun as Earth, and Mars roughly orbits about 1.5 times the distance, the distance from the sun. Sorry, Earth's distance from the sun. Mars's distance is about 1.5 times that. I don't know why that was so hard to say, but you know what I mean. Anyways, so the first thing to think about in terms of climate is just the way that proximity to the heat source affects the temperatures of the planets. And the beginning understanding of climate is very simple. Climate is just the average temperature of a place, be that a planet or whatever. And the closer you are to the heat source, of course, the warmer you're going to be. And we all have an intuitive sense of that. Think about sitting around a campfire at night. If you're cold, you move a little closer to the fire. If you're hot, you move back a little bit. And basically we can calculate very simply with very simple physics what we call the equilibrium temperature of any object in space, just based on the distance from the star and the reflectivity. Brighter objects will also be cooler and darker ones will be warmer. We call that albedo. And you're also familiar with that intuitively if you think about walking on a road at night, walking on a road during the day, barefoot in the sun. The white lines will be cooler than the black pavement because of that albedo effect that bright reflective surfaces stay cooler. So there's sort of we call that equilibrium temperature, just the temperature you would calculate for an object based on its distance from the sun and its reflectivity. And that's really simple to calculate. So climate is simple, right? Wrong, because of the effect of atmospheres. These planets are not just solid objects in space, they're also surrounded by atmospheres, and that's where climate gets complicated because of something you know something about, I'm sure, the greenhouse effect. If I can have the next graphic, just to sort of review very simply, of course, the greenhouse effect is what you get when you have a star and a planet, and there's visible radiation coming from the star, sunlight, and that gets absorbed by the surface of the planet. The surface of the planet heats up, and it radiates infrared radiation back into space. That's just your basic thermal equilibrium I was talking about. What makes it more complicated, of course, is the atmosphere is not transparent to all radiation. It's full of greenhouse gases. On Earth, of course, CO2 is the famous one, but there are methane and sulfur dioxide. There are many other greenhouse gases. And those greenhouse gases mean that infrared radiation can't simply just go back out into space. A lot of it gets trapped in the atmosphere and then re-radiated back to the surface and sort of bounced around. And that composition of the atmosphere, where there's greenhouse gases, is what makes climate complicated. Planets heat up, and the extent of the greenhouse effect, the amount to which a planet heats up, depends on both the total amount of atmosphere, how thick an atmosphere that planet has, and crucially, what portion of that atmosphere is composed of greenhouse gases, because other gases, the nitrogen and the oxygen that make up most of Earth's atmosphere, are not greenhouse gases, meaning that just as the visible light can pass through them unimpeded as it heads towards the Earth, the infrared light also passes through those non-greenhouse gases. But the greenhouse gases are what heat a planet up with that blanketing effect. So now let's go back and think about the other planets. Next slide, please. So through our exploration that we've been able to achieve since we just started sending spacecraft in the 1960s. And we've had, as you know, a lot of spacecraft that have gone all the way to the surface of Mars, and we've had a few spacecraft that have also managed to go to the surface of Venus, which is a much more difficult task to get to the surface of Venus. And you can see why on this graph. This is a graph of, this is altitude over a planet's surface, and this is temperature. And what this is showing us is basically what we call the vertical temperature structure of a planet. So first of all, here's our familiar Earth, and this is the troposphere where we live. And as you know, it gets colder as you go up. That's why, you know, you go up to the top of the mountain, it gets colder. But then that turns around in the stratosphere, and it actually gets a little bit warmer. That's because of the ozone layer heating things up, and then it gets colder again. But this slope here between the surface temperature and actually this arrow here is, I was talking about equilibrium temperature before. This is the temperature Earth would have without any atmosphere, just based on the sun's heat, the sun's radiation. So this difference here is the Earth's greenhouse effect between the surface temperature and this equilibrium temperature. And you see it's not very large. It's a little less than 20 degrees on Earth, that greenhouse effect. But that's crucial here. We're used to thinking of the greenhouse effect as something that we're worried about and is dangerous, and that's because too much of a good thing is dangerous. But without the greenhouse effect on Earth, our planet would be uninhabitable for life like us. This little bit of greenhouse effect is what keeps Earth above freezing, so it's actually a really good thing. You just don't want to have too much of a good thing. But contrast that to the greenhouse effect on Venus. Venus is really hot, and this is Celsius, so it's about 475 degrees at the surface. In Fahrenheit, which you might be more familiar with, it's about 900 degrees at the surface on Venus, all the time, everywhere. And so the greenhouse effect on Venus is huge. Here's the equilibrium temperature of Venus, Venus without a greenhouse effect. So you see that it's just hundreds of degrees of greenhouse warming on Venus. So much, much larger than the greenhouse effect on Earth. And the reason for that is twofold. Do you remember I said the greenhouse effect on a planet depends on the mass of the atmosphere and the composition of the atmosphere, how much of it is greenhouse gases. Well, Venus has both a really massive atmosphere. The surface pressure on Venus, we've learned, is almost 100 times the surface pressure on Earth. It's about 90 times. So to get to that much pressure on Earth, you'd have to go about almost a mile under the ocean. That's how much pressure there is. And that atmosphere on Venus is made out of almost all carbon dioxide. It's about over 96% carbon dioxide. And you remember carbon dioxide is a greenhouse gas. So you have an atmosphere that's incredibly heavy, thick, and almost all greenhouse gas. So Venus is sort of the extreme, the ultimate in a ridiculously strong greenhouse climate, and that's why it's so ridiculously hot there. Now Mars is interesting because you see Mars has a very tiny greenhouse, almost none. There's the equilibrium temperature and there's the surface temperature, very small greenhouse. And the interesting thing about Mars, its atmosphere is also made out of carbon dioxide, almost all carbon dioxide. So it is all greenhouse gas, but it's very, very thin. It's the opposite of Venus. It's about 1% of Earth's atmosphere. So you'd have to go very high up in a stratospheric airplane on Earth to get to a level where the air was as thin as it is on the surface of Mars. So there just isn't enough gas on Mars to support much of a greenhouse. But the really cool thing about this graph, in addition to the fact that it illustrates in just one handy graph the major differences in climate between the planets, but it also validates that our climate models work. In other words, if our understanding of climate is right, in terms of the basic physics of just what I was describing before, blocking infrared light and how that heats up an atmosphere and how that should change the temperature at different heights above the surface, then we should be able to predict that not just for the Earth, but for the other planets as well. And it's comforting to realize that when we go to those planets and we measure that temperature profile, we measure the temperature at different depths above at different altitudes above the surface, that what we find is exactly what we would predict from our climate models. And that's really, to me, that's comforting, because climate modeling now is not just something that we do because it's cool and interesting and we're curious. That's all true, but it's also a survival tool. We have to be able to accurately understand what the climate on Earth would be if we change something in the atmosphere, because our survival depends on getting that right now. But how do we know that we're doing that physics right? Well, one way to know that we're doing it right is if that model works on another planet and we can predict what the climate should be, and then we go and measure it, then we can say, oh, our climate models are capturing some aspect of reality. They really work. And to me, this graph, which shows the models and then the fact that what we measure is exactly the same on Mars and Venus, it's sort of comforting. It means, yes, we actually do know how to model climate, not just on today's Earth, but on an altered Earth with a different atmosphere. And that gives me encouragement that we're doing something right. Next slide, please. So this is important because we always talk about modeling climate into the future, but how do we do that? We don't have a crystal ball, so how do we see the future? What we do have is climate models, and this over on the right here shows the result of one of our sophisticated climate models, and you can see as the years tick by the changes in surface temperature getting disconcertingly warm as we move into the future. This isn't written in stone. These models, of course, depend on what we collectively do with our energy and other aspects of our civilization. Nothing's written in stone, but the point is that these studies of the other planets sort of validate that these climate models are actually doing something real. And so in the absence of a crystal ball, it's important that we in any way we can, we validate and we make sure we do know how to model climate. And thus far, our studies of neighboring planets are encouraging in that regard. Not only that, but we've learned a few things, and I won't go into a lot of detail here, but we've learned a few things by studying climate on Mars and Venus that we were missing in our Earth climate models. So the models get better because we find some subtle things that weren't quite right, and we improve our Earth climate models by tweaking them through things that we've learned about studying the other planets. Okay, so that's climate today on Venus and Mars and how it compares to Earth. But what about how the planets got to be the way they are today? When we study Venus and Mars on the surface, and we look at their geology and look for clues to the distant past, what we find is a lot of evidence that both of those planets used to be a lot more Earth-like in the distant past than they are now. What you're seeing here, this is a river delta on Mars in a place called Jezero Crater, which is one of the places we're exploring now with one of our rovers. And you can see this is basically where a river has flowed out onto the surface and spilled water out. And you can see this was a long time ago. Here's an impact crater, a giant impact crater superimposed on this ancient river delta, filled in with sand dunes of blown dust. So this is ancient. This tells us that this happened a long time ago. All this is eroded. It turns out that this river flowing out and forming this delta into this crater, this flowed billions of years ago. So when we explore Mars in detail with our rovers and our other spacecraft, we see many, many signs of water that flowed there, but it was a long time ago. It was when Mars was a young planet billions of years ago. Some of this evidence for ancient water includes these giant channels, what we call outflow channels that we see from orbit, and dried up river channels that we see from orbit. Lots and lots of layered sediments. Think of sort of Utah, places where there are ancient sedimentary rocks laid down by ancient water and then eroded away. When we go to the surface with our rovers, in fact, we find rocks that we can go right up to and analyze their chemistry. And this is one of the rocks that we found with one of our first rovers on Mars, with Curiosity. And in fact, this was one of the first clues that we really were exploring a place of ancient flowing water, because this rock is made out of a mineral called jarosite, a sulfur-based mineral that we don't know how to make any way except for it's deposited in flowing water. So the more we look at these rocks up close and analyze their chemistry with our rovers, we find signs that, yes, this was a watery place billions of years ago. And over here, also with our rovers, we see, in fact, we go down into some of these craters, and the walls of the craters are these layers and layers of ancient sediments that were laid down a long time ago when Mars was a watery place. So the more we've explored Mars, the more we understand that in its infancy, when it was a young planet billions of years ago, it was a much more Earth-like place. And that's fascinating because around 4 billion years ago, when the origin of life was happening on Earth, we think Mars had similar conditions. In other words, warm, nutrient-rich waters flowing on the surface and pooling on the surface on a planet that could have had an origin of life, just like Earth did. And so that also creates a mystery. What happened to the water on Mars? If it was once a warm, wet place, why today is it a frozen, dried-out desert? Next slide. So we can also think about ancient Venus and how Venus got to be the oven that it is today. Now, Venus is a harder place to explore than Mars, and that's because of these clouds. Venus is constantly shrouded completely in clouds. So you cannot see the surface from orbit. You cannot see the surface with a telescope. And furthermore, we've learned, because some spacecraft have made it down through the clouds, we've learned that the surface is that incredible 900 degrees, so it's not easy to operate anything down there. So it's hard to see the surface because of the clouds. And if you go below the clouds, your machine's not going to last very long. Given that, it's quite a feat that we actually do have a small number of photographs taken at the surface of Venus. These were all taken by the Venera spacecraft sent by the Soviet Union in the 1970s and 1980s. And the Soviet Union, one of their big successes in space was that they had a really successful Venus exploration program. And they remain the only country ever that has ever successfully landed spacecraft that survived on the surface of Venus. They did it just a handful of times, but they took these photographs, and from here you can see that at these sites, what you see are these sort of eroded, flat, platy rocks that look very much like kind of ancient eroded lava flows with a little bit of fine sediment around them, but mostly they look like ancient lava flows. And that is confirming a picture that we have of Venus as a planet with a long volcanic history on the surface. The Russians did manage to land a handful of spacecraft, and then in the 1990s, there was an American spacecraft called Magellan, which managed to map the entire surface using radar. You cannot see the surface through the clouds with normal cameras, but with radar, you can penetrate right through the right through the clouds. And this is what the surface looks like as taken by the Magellan spacecraft. And you can see that a lot of it are these very smooth volcanic plains. We call those flood basalts. Think of the Pacific Northwest in the United States, are these very voluminous, smooth volcanic plains. And then smaller areas are these very rough highland areas, and there's some giant volcanoes, sort of Hawaiian-type volcanoes, and very few impact craters. If you look around, you can see maybe one, there's one right there. But compared to Mars, which is full of craters, there are almost no craters on Venus. Some of that is because the thick atmosphere screens out the fast-moving objects and they burn up in the atmosphere. They can't reach the surface. But a lot of it is because Venus has a much younger surface. It turns out that the average age of this surface is less than 1 billion years, which is much younger than Mars and a little bit older than Earth. But it basically tells us that Venus has been geologically active more recently, that it's been repaved by volcanic activity, almost the whole surface. And that's really interesting for what it implies about Venus today probably being volcanically active, which is one of the things we want to explore with our future spacecraft. But it also means that it's really hard to reconstruct the deep past of Venus, because unlike Mars, you can't just go and say, oh, there was a river there 4 billion years ago, because you cannot see what the surface was like 4 billion years ago because it's been paved over by more recent activity. So we've had to kind of piece together the ancient history of Venus, but we have found some clues in the atmosphere which suggests to us, again, that Venus started off probably as a much more Earth-like place. And we think that it started out with oceans of liquid water, just as Mars did, and that somehow those oceans were lost, and Venus ended up as the sort of hellhole that it is today on the surface. If I could have the next slide. So one way to ask the question of what happened to Mars and Venus, we can ask, how did Mars and Venus get so extreme? But another way to ask the question is to come back to Earth and say, what is it about Earth that has allowed its climate to stay so constant, so steady for billions of years and support life, when both the neighboring planets went off in some climate catastrophe and became uninhabitable on the surface? And on Earth, it turns out that a lot of what allows our planet to stay in this sort of moderate climate that supports life has to do with the carbon cycle. Earth actually has kind of a natural thermostat that operates over many millions of years. Here's how it works. There's a small amount of CO2 in Earth's atmosphere that kind of keeps the climate the way, at just the right temperature, above freezing, but not too hot, so that life can exist. And the main source of that CO2 is volcanoes. Volcanoes are always going off and always supplying carbon dioxide to the atmosphere. So why doesn't the carbon dioxide just build up in the atmosphere and make the planet hotter and hotter? A lot of it has to do with rainfall. There's rainfall always happening, and that absorbs carbon dioxide. It dissolves carbon dioxide. It makes something called carbonic acid dissolved in water. And that rainfall pulls carbon dioxide out of the atmosphere. It runs along the surface of the rocks, dissolving the rocks, and it ends up in the ocean and ultimately ends up making carbonate rocks on the floor of the ocean. Think of like the white cliffs of Dover, white, chalky carbonate rocks. That's where the carbon from the atmosphere ultimately ends up. But of course, it doesn't just stay on the ocean floor, because Earth has plate tectonics. Earth is always recycling its surface into its interior with the cycles of plate tectonics. So those carbonate rocks ultimately get sucked into the interior of the Earth along with the rest of the ocean floor, and then eventually inside the Earth, they're subjected to the pressure and temperature of Earth's interior, and the carbonate rocks are broken up, and the carbon is released again as CO2. So that's the long-term carbon cycle. CO2 coming out of volcanoes, rainfall pulling it out of the atmosphere. It ends up in the ocean as carbonate rocks, and then over a long period of time, they get broken up and it gets released again as CO2. So that's the carbon cycle, but that's not a thermostat. What makes it into a natural thermostat is the effect of climate. That when Earth heats up, the hydrological cycle that produces that rainfall increases. There's more rainfall, And the chemical reactions that we call them weathering reactions that pull CO2 out of the atmosphere, they speed up also in higher temperature. So the hotter the planet is, the more this cycle is pulling CO2 out of the atmosphere, and it tends to naturally cool it off. Now, the reverse is also true. There have been times in Earth's history when the planet goes through a cold cycle, a glacial cycle, an ice age. And when that happens, this part of the thermostat turns off. The rainfall stops. And even if there is precipitation, the surface is frozen over so that none of those chemical reactions with the rocks happen. So when it's cold and frozen over, this part of the cycle stops. But the CO2 keeps building up in the atmosphere. So there's a natural thermostat. When it's cold, the carbon dioxide increases in the atmosphere because the volcanoes keep going. They don't care about climate. When it's hot, the system draws down CO2 and cools the planet off because the hydrological cycle responds to climate. So all of that means that over millions of years, Earth has a natural climate thermostat, and that's what's kept our planet habitable, a good place for life over all this time. Now, by the way, this isn't to say, so don't worry about climate change, folks, because the Earth will take care of itself and return climate to normal. That's true in a couple million years. No matter what we do to the climate, this cycle will pull it back in a couple million years. But we don't have a couple million years, so it doesn't really help us, but it helps the biosphere in the long run. But the point I want to make here, again, is going back to comparing to the other planets. We think that this is how they all operated when they were young, because when Venus and Mars had their oceans and had rainfall, they probably also had a climate thermostat like this. But the climate thermostat broke. The climate thermostat broke on Venus and Mars, and it broke in different ways on both those planets. Going to the next slide, on Mars, what happened was the volcanoes died out. Mars is a small planet. It has these huge ancient volcanoes. We see billions of years ago they were active. But what happened was, if you go to the next slide, because Mars is a small planet, its interior lost its heat. And without interior... okay. I think there was a slide we missed, but that's okay. Basically, the volcanoes on Mars... Oh, there it is. Yeah. The interior... If this is a cutaway showing the interior of Mars, and a small planet loses its heat faster than a large planet. And we think that because of that, the volcanoes died out young. And when the volcanoes died out, there was nothing replenishing the atmosphere on Mars. And so Mars, also being a small planet, doesn't have much gravitational pull. And so the oceans were basically lost to space. The volcanoes died out. There was nothing to replenish the atmosphere on Mars. And so the thermostat stopped because there was no source of carbon dioxide, and it lost its atmosphere and lost its water. So today, Mars has very thin atmosphere, it's frozen, and there's no water. That's basically what we think happened to Mars. Now, if we go to Venus, what happened on Venus was that we think it also started out with an Earth-like ocean, but there was what we call the runaway greenhouse. You know what the greenhouse is. But the runaway greenhouse is when a planet's a little bit closer to the sun than Earth, as Venus is, then you get this positive feedback. The surface temperature is a little bit hotter. That causes evaporation. You know that. If you have a glass of water out on a sunny day, it will evaporate. Heat evaporates water. But the problem is, water vapor is itself a powerful greenhouse gas. So when the higher surface temperature means there's more water vapor in the atmosphere because of evaporation, that means there's a stronger greenhouse. But a stronger greenhouse means the temperature's higher, which means more water evaporates, etc. And it runs away. So you have a runaway greenhouse. And we think that's what happened to Venus. But the big mystery for Venus then is, first of all, did that really happen? Did it have an ancient ocean? And when did that happen? How long ago did Venus lose its ocean? These are still huge questions we have that motivate our next missions that we want to send there. So, next slide, please. So in order to try to understand better the actual history of Venus, one thing my colleagues and I have done recently is we've applied a tool called a general circulation model, or a GCM, that we use to model climate on Earth, but we've finally been able to apply it to Venus. Now, you've heard about these GCMs. This is how we do climate modeling on Earth, where you basically break the atmosphere up into a grid of lots and lots of little boxes, and then you model all the different physics that are happening, the solar radiation and the formation of clouds and everything, and you pass it between these little boxes, and you model the whole system of the atmosphere. And we know this works on Earth because we've been able to validate it, but if it really works well, we should be able to adapt it to other planets. It's been a little bit hard, but we've recently been able to successfully, we believe, do it for Venus. And we've run GCMs to this and applied them to this problem of how did the climate change on Venus. And we found what we think is a pretty surprising answer. If I could go to the next slide. When you do this for a slowly rotating planet like Venus, because Venus rotates really slowly, hundreds of Earth days just to go around once, and it rotates backwards, what we find is that the clouds do something weird. They all gather on one side of the planet. And you end up with a Venus that's permanently cloudy on the sun-facing side and permanently clear on the anti-sunward, or the night side. And that is perfect conditions to keep Venus cool for billions of years. It acts like a sunshade. In other words, the bright reflective clouds on the sunward side reflect solar energy so that keeps the planet cool, but also having it clear on the night side means that the infrared radiation can escape to space and cool the planet off at night. Just as you've experienced on a cold winter night on Earth, when it's cloudy, it stays warmer at night, and when it's clear, it gets colder at night, is because clouds block infrared radiation also. So this is perfect conditions to keep a planet cool, and we think that this result means that Venus may have had oceans for billions of years. This is a surprising result, that for most of its history, it might have had Earth-like oceans on the surface. So if we can go to the next slide, that's kind of an enticing picture, because what it might mean is that for much of the history of our solar system, we had these two planets, Earth and Venus, right next door to each other that may have been oceanic. And if you think of what happened on Earth during all that time, the formation of life, and then the formation of photosynthesis and more complex life, and all these different changes for billions of years, Venus, during all that time, might have had an ocean right next door. And the two planets could have even been exchanging life, because we know that occasionally meteorites get bounced between planets. So we don't know if this is true, but it may be that Venus was a habitable planet right next door to Earth for much of its history. In order to find out, we've got some new missions that we're sending to Venus in the next decade. And I'm really excited about this, because my colleagues and I have been proposing missions to Venus for a long time and getting rejected. But now we have 3 new missions, all approved to go to Venus. So we're calling this the Decade of Venus. One of them is a European Space Agency mission called Envision, which is going to be an orbiter, which will take new radar and infrared images of the surface and even the subsurface and study the upper atmosphere. And another one is an orbiter, an American orbiter called Veritas, which is both of these are going to launch around 2030, and they're both in progress now towards getting built and approved and so forth. And then we have another mission, which, next slide please, which is an entry probe mission called Da Vinci. And this is the one that I'm actually most involved in, and I'm really excited about it. We're going to drop a probe right into the atmosphere. Here you see it on the heat shield, but then when it comes out of that heat shield, it's basically a spherical probe. It's a 1-meter titanium probe that we drop right through the atmosphere, and it will tell us what's in the atmosphere, and it'll even photograph the mountains as we approach the surface. And I think this is going to provide a lot of the answers to this question of, did Venus really have an ocean, and how ancient was that ocean? And it'll make us give us a much more sophisticated knowledge of this comparison between Venus and Earth. So stay tuned, because this is the decade of Venus. I just want to end up now by returning to Earth a little bit and talking briefly about some climate change on Earth and how that's illuminated by thinking of the other planets. Next slide, please. If we think about the different kinds of climate change in our own planet's history, of course, there are kinds of changes that we don't see on the other planets. This is a cyanobacteria, and I have this here to remind us of the fact that we humans are not the first species to ever change the climate on a planet. In fact, 2 billion years ago, the cyanobacteria discovered a new energy source and were so successful at exploiting it that they poisoned the whole planet with a dangerous gas. That energy source was photosynthesis, and that dangerous gas was oxygen, which caused a lot of species to go extinct at the time. And they crashed the climate, probably, and caused this snowball Earth, caused the climate to completely freeze over. So we're not the first species to sort of mess up the planet. What we are is the first species to do it with some knowledge of the fact that we're doing it, which gives us some responsibility, and but hopefully also some promise of being able to do things better. Next slide, please. Another kind of natural, a climate change that's happened on Earth that does happen on other planets is what we might call natural disaster climate change. This is Yucatan, Mexico, where there's a 93-mile long crater that we discovered that's buried under the surface of the land here, that was caused by an asteroid that hit the planet 65 million years ago, wiping out the dinosaurs and causing this huge climate disaster because, here, we're going to see the animation here of when this thing hits. Whoa. And what it did was it raised a huge dust cloud into the atmosphere, which absorbed solar energy high up in the atmosphere and cooled the surface and caused such a climate disaster that it led to a mass extinction. So this is a kind of what we could call a natural disaster climate change that happens on all planets. But there's a new kind of climate change on Earth too, next slide please, which we can call Anthropocene climate change. And Anthropocene is the term that we're using now for this new geological epoch of Earth history where humans have become a force of planetary change. And we're all, if we're paying attention, concerned about this and trying to learn as much as we can, as quickly as we can, about the history and nature and future of our planet so we can do a better job managing this Anthropocene climate. And one of the ways we do that is by studying the other planets. So I'm going to just end up now with a couple of lessons about Earth climate that we've learned from studying the other planets. So next slide, please. With Mars, one of the things we learned about its climate is that there are occasionally these huge global dust storms where they start in the southern hemisphere summer and they spread around the entire planet. And about every 2 years, Mars is enveloped in a totally encompassing global dust storm. And the scientists who were studying that, the same scientists who learned to model global dust clouds from studying the climate of Mars, were the same scientists who discovered the climate effect of this asteroid that wiped out the dinosaurs on Earth 65 million years ago, and then using the same climate models, if I can have that little mushroom cloud there, they figured out the theory of nuclear winter. Because it turns out that when you fill an atmosphere with dust and smoke, as you would in a nuclear war, that you do something horrible to that planet's climate. And the discoverers of nuclear winter were the same scientists who modeled these global dust storms on Mars. And that discovery was really important, even ultimately, in helping to end the Cold War arms race, because we realized through this discovery that nuclear weapons are in fact not weapons. You can't win a nuclear war. They're sort of suicide machines, and this proved it. And then finally, a couple of climate lessons from studying Venus. Next slide, please. Just really quickly, there are several of our most difficult environmental problems that it turns out Venus is a natural laboratory for studying. I've already talked a lot about the greenhouse effect, and Venus, of course, is an extreme example of climate change, and by studying climate on Venus, we've learned a lot that can help us understand the subtleties of climate on Earth. There's also, you've heard about acid rain, and those clouds of Venus I didn't mention that cover the whole planet, they're made out of concentrated sulfuric acid, H2SO4, battery acid. So by studying the chemistry of the clouds of Venus, we learned a lot that has helped us mitigate acid rain on Earth and things like scrubbing sulfur dioxide out of chimneys. We've actually done better with acid rain because of what we've learned. And then finally, I want to mention the ozone hole. You know about the ozone hole because of these refrigerants, chlorofluorocarbons, getting up into the stratosphere and messing up the ozone layer. But what you may not know is that the way we discovered that we were doing this to our own planet was partially by studying the upper atmosphere of Venus, because there's a mystery in the upper atmosphere of Venus. There should be more oxygen, and there isn't. And some scientists figured out that's because there's chlorine in the upper atmosphere of Venus, and chlorine eats oxygen molecules. And some other scientists read that paper about Venus, and they said, oh, that's interesting, but hey, wait a minute, what about all this chlorine we're putting up in Earth's stratosphere from these chlorofluorocarbons? Uh-oh, wait a minute. And they realized that that was what was harming the ozone layer, and they sounded the alarm. So by studying Venus, we discovered something really dangerous that we were doing to Earth. But this story actually has kind of a positive ending, because once we discovered the ozone hole, there were global debates and conversations about it, but ultimately there was a global agreement made, something called the Montreal Protocol, where all the major industrial nations of the Earth got together and realized they needed to do something about this, and they made an agreement to stop producing those chemicals that were harming the ozone layer. And guess what? It's worked. It's a success. The ozone layer is on track to being fixed. So I think this is a really important lesson, because it shows that we do have it within us to make a global response to realizing a global problem, and that by studying the other planets, we can become wiser about what's happening on Earth, and we can become the kind of species ultimately that knows enough about our planet so that we can do a better job of managing ourselves here on the Earth. So I'm going to stop there because I've taken up enough time.